C.C. May, Chang Mei, and Ola Madsen, who will also be talking this afternoon, really provided me an enormous amount of support in learning how to operate at MIT. It was a different situation than Scripps, as you might have gathered by sitting out at lunch today. And Chang provided both intellectual and financial support to help get a program going there. He and Nick Newman took me under their wings, which are quite substantial, and helped me get started at MIT. So I have an enormous debt that's never quite been repaid to Chang. The other advantage of having Chang as a colleague was that I could advise students who had been through his waves classes. And so I could be sure that the students that were going to work on wave-related research with me had been through a pretty rigorous course on the theory of wave mechanics. And that was a great advantage too. And finally, anybody who has seen my office knows that it has a lot of paper everywhere, and almost every horizontal surface is covered. And for a while at MIT, my office was right next door to Chang's. And Chang had similar office habits to me, and even went to the extreme of actually tying, I think it was one of your books on integrals, Chang, or it could have been Abramovich and Steger, I'm not sure which. But at one point he had it tied by a long string to his desk, so that if it ever got lost under this pile of papers, he could just pull on the string and rescue it. I never quite got to that point, but at one point when I was here before I left for MIT, John Miles, whose office was next to mine at IGPP, came in and saw my desk and said, "How can you work in this mess?" So I've never completely figured out how to keep a clean office.
Just completely.
Anyway, it's an enormous pleasure to introduce Chang Mei to those of you who don't know him.
Indeed, Ken has been my colleague at MIT for 10 years. During those 10 years, he not only extended his fabulous work on Benjamin Fair instability of waves, but he essentially laid the groundbreaking start of wave-breaking studies, which has become his signature contribution in the field. And I can understand why he left MIT to La Jolla, because the intellectual as well as natural environment are just too good. And I think indeed Ken and La Jolla are made for each other. I'd like to take this opportunity to congratulate him on his 70th birthday. And I'm going to give the talk on two problems that are sort of related. It may seem to be unrelated in the beginning. The first is on wave power extraction. As many of you may have imagined, that there's lots of power in principle in the ocean, and to extract power from the waves is a dream of humanity for centuries. And the other is on blood hammer, and I'll explain what blood hammer is. Okay, first of all, let me go to the first topic on power extraction from waves. Just to give you some preliminary, just to have some preliminary idea, waves even coming at an oblique angle, eventually the wave crest becomes parallel to the shoreline. And in a plane wave, the power influx is proportional to the amplitude squared times the group velocity. And you can convert it into another expression, the proportion of the amplitude squared times the period. Suppose the typical wind swell, the period is 10 seconds or so. Now, if we use this crude estimate of average amplitude of 1 meter, say, then the power flux per meter could be 40 kilowatts. This is about the approximate power potential in the western coast of the United States. In Australia, it can be a lot bigger. Now, you can see that if 1 meter gives you 40 kilowatt, to give you the capacity of a nuclear power plant, it takes about 10 kilometers length of coastline to install power stations. So this creates problems, of course. Now, there are many different kinds of wave power devices. Let me just give you a few of them. Okay? The simplest one is the single buoy, which heaves up and down, and therefore pulls a linear electric generator fixed at the bottom, and the oscillation creates electricity in principle. This has the advantage of being independent of the direction of the incoming waves. But this is the case only for single buoy, not for an array of buoys. Okay? Then there's another interesting thing called oscillating water column. It uses the fact if you have an opening of a structure like this, the water surface inside can go up and down in order to push air through a turbine. This turbine is inside, is outside the water, therefore it's easy to maintain. And in fact, this turbine can be, even though the flow is oscillatory, if the turbine is turning, it can maintain its rotation in one direction. This principle is similar to that of a dragonfly. You know, the dragonfly, although the dragon winds fluctuate up and down, but nevertheless it can maintain forward speed. The third is a series of rafts. The relative rotation between two adjacent rafts can be made use of to create wave energy. Now, a more modern version is a Polaris, which has been technologically advanced very much in recent years. Ideally, this kind of a 3 or 4 section raft can be made into an array to create a waveform. But all of these are ideas. But the basic idea of all these, of nearly all of these, is resonance. In order to create even optimum wave power extraction rate, it takes resonance is the key. Now let's use a simple example of a single buoy. Now the single buoy, the energy extractor can be modeled mathematically as a dashpot. So this is a 1 degree of system of spring dashpot system, the spring being provided by buoyancy force. Now we use a linear model to model the damping force, namely power extraction effect. The force on of the power takeoff device on the buoy is then proportional to the velocity of the heaving motion. Now Newton's law can be easily written down for this 1 degree of system, and the power extracted can be written down like this in a very simple way. This Fd is the scattering force due to the incoming wave. Now you can see that in order to have the maximum of wave power, you have to have this factor to be 0. Namely, the buoyancy has to be balanced by the inertia force, where m is the mass of the buoy and mu is the parent mass of the buoy. And not only that, the extraction rate of the power takeoff must be equal to the radiation damping rate. In other words, the two conditions for maximum wave power at any frequency is that the buoyancy force must be balanced with the inertia force, and the extraction rate cannot be too large nor too small. It has to be in such at this number. Now this is for one single frequency. And at this single frequency, the maximum power capture is this quantity. Because the incident power per unit length in the plane wave is this quantity, the ratio defines the capture width. This capture width is 1 over the wave number, namely it's proportional to the wave length. And the product of k times the capture width, ideally, at the optimal situation is 1. Namely, the capture width can be nearly 1/6 of the wavelength. Okay, but this is at the one single frequency, but the waves are not, ocean waves are not of single frequency. Now, if you have, because waves are of waves have spectral width, let's consider the effective size. For this, A is the radius of the buoy, H is the depth. This is a very large, for 0.43, it's a very large buoy. 0.717 is a small buoy. You can see that the oscillation amplitude has a maximum at resonance, but the resonant peak is at a long wave frequency if the radius is very large. Its resonance frequency will occur at a high frequency if the radius is very small. Therefore, if you have a typically very small buoy, like 5-meter diameter, it won't resonate in ordinary sea waves. You have a reasonably large one in order to have it oscillate, resonate at the 8-second frequency. This is a very large one, but normally people do not, designers do not use this kind of model. So the size has a large effect. Okay, this is, for this reason, there's a lot of limit on the wave part devices, is how to make the efficiency very high for a broad range of frequencies, not a single frequency. Okay, now there's a recent development which seemed to be very different in idea. It still works on resonance, but uses a very exotic idea. This was invented by Francis Farley and his colleagues at the University of Southampton. Farley is an astrophysicist, a 90-year-old astrophysicist. And he has this idea, which is that he wants to use rubber tube and to form a tube of, it was a very long rubber tube, but several wavelengths long. The diameter can be several meters, and the thickness of the wall is maybe 10 centimeters or not very large. Now, if waves are passing over from left to right, then it can cause this rubber wall to move up and down and in a waveform. This waveform will create waves in the fluid inside. This fluid inside will be driven to the end in order to drive a turbine which turns into one direction. This turbine, invented by the Irish inventor Wells, called Wells turbine, even in oscillating flow, it rotates in one direction, unlike the ordinary hydraulic turbine in water. Okay, so this is the idea. So Farley has actually done the. Let me see whether I can have this movie. You can see the bulge waves, the waves propagating from the top of the screen to the bottom. There is a wave, the tube walls deform, so that there's a wave propagating from the top to the bottom. The voice is that of Francis Farley at the time he was 90 years old. Okay, and okay, now let me go to the ideal. Ultimately, they want to have an array of these things because when they're all moored, they can move around like snakes. Therefore, they call it Anaconda. Okay? So this system, at that time, they were doing experiments. And I was fascinated by it. I did a theory for it, and which I think is kind of fun to do this. Whether or not it'll become a reality, that's uncertain so far. Okay? Now, it turns out that their idea is really based upon the blood flow in the blood vessel. We know in the blood vessel wall is elastic. Therefore, even if the blood is quite incompressible, waves can propagate through the blood vessel. Okay? And the typical equation governing the pressure in the fluid, in the vessel, is this wave equation, where this wave velocity depends on the elasticity of the wall and the thickness of the vessel wall and the radius, mean radius of the vessel. Therefore, and not only that, if the waves of a certain frequency, it will give rise to a certain wave number, which is of this kind of quantity. So, if you want to have resonance inside this blood vessel, you only need to choose the radius, choose the elasticity, choose the wall thickness in such that the natural frequency of the tube matches with the natural frequency of the wave. Okay? And also, it can be shown that the radial extension A is versus blood pressure is of this relationship. This is sort of elasticity relationship. And at resonance, it can be shown that for usual tubes where the radius is much smaller than the wave number, this ratio can be very small. In other words, a small wave pressure can excite very large pressure inside the blood vessel. Okay, based on okay, and then not only that, because of the slenderness of the tube, it can be shown that the effect of wave scattering and wave radiation are negligible. The only effect of waves on the fluid in the blood vessel is essentially to create resonance. The wave loss, the radiation loss, and so forth is very small. Based upon this, it's possible to write down the equations of motion. Let me give you a little bit of a background of the theory. Now, first of all, the conservation mass is this, where S is the cross-section area. But this cross-section area depends not only on the mean radius, but on the distension of this is the radial displacement of the wall. And as a result, this fluid mass equation has some small nonlinearity, which is proportional to the ratio of the distension to the mean radius, which is usually very small. For example, small a can be tens of centimeters, r can be meters. And the conservation momentum, because we include nonlinearity, we have to include some convective inertia. And in this kind of situation, the friction is not negligible. Therefore, we have a wall stress, which we'll discuss a little later on. And there's a solid mass equation, namely the instantaneous radius times the net area of a solid mass at any one cross section is the same, whether whether without distension or with distension. It's the same thing. Therefore, the H, the instantaneous thickness of the wall, actually changes with the stretching of the wall. And the solid momentum, it can be shown that for usual long waves in water waves, the inertia is negligible. Therefore, the pressure, blood pressure inside, fluid pressure inside, and the distension are in a quasi-static equilibrium, which is called pressure-area relationship. This relationship depends very much on the structure itself. According to the experiments of Foley and so forth, it is given by this sort of a nonlinear equation. And in fact, people at MIT, Shapiro and others have done many experiments for rubber tubes to simulate, to get to this kind of relationship. The relationships are qualitatively similar, although quantitatively different. Okay, with these relationships, it's possible to deduce a dimensionless equation like this. Now, in a normalized distension, which is radial distension divided by the mean radius, is governed by this nonlinear wave equation with weakly nonlinear effect, plus the effect that due to the friction on the wall and due to forcing of the external pressure. Now, it turns out that both forcing from external waves as well as the damping are of small magnitude, and nonlinearity is assumed to be of equally small magnitude. Therefore, this equation is a quasi-linear, nonlinear, slightly nonlinear, equation governing the wave motion inside the tube. And now, we know that in order for a system like this, in order to achieve nonlinearity, it takes a long distance. Namely, the pipe has to be very long, several wavelengths long, in order to create significant resonance. So we assume that there are two kinds of scale. One is x characterized by the wavelength itself. One is a long length characterized by the total length of the tube. Okay? We assume that the two are vastly different. There's a sharp contrast. And we assume the water wave pressure is slightly detuned from the natural wave inside the blood vessel. The detuning wave number is called capital K. In that case, we can assume some sort of multiple scale expansion, assume that the displacement to the leading order and the higher order, they are a function of the short scale as well as the long scale of nonlinear development. And because of nonlinearity, even if the incident wave is simple harmonic, the resultant wave is a multiple harmonic. Therefore, we assume that it is an infinite number of harmonics. And with this, we can easily compute we assume sort of a quasi-laminar eddy viscosity model using the Stokes modulator approximation in order to compute the wave stress, the shear stress. And with this then, it's possible to deduce over a long time the evolution of the amplitude of nth harmonic is governed by this nonlinear ordinary differential equation with nonlinear terms and with the linear forcing with a little detuning and with the viscosity. Initial condition is that at the beginning, at the stern of the tube, we have no amplitude. The amplitude will grow as you go further down the tube. Okay? This equation turns out to be an extension of a famous equation, nonlinear optics. We know that in nonlinear optics there's a phenomenon called second harmonic generation. Because of nonlinearity in the material, high intensity light can change color from one color to the other color. And the most famous Nobel Prize winning result was the second harmonic generation, whereas here we have a harmonic generation of many different orders. Okay? This can be easily solved. So then we try to solve this. Let me show you some of the preliminary results. For example, let me find the effective detuning. Because we know if in all the resonance system, if detuning is very large, then the efficiency is low. Then this is shown here. Suppose detuning is zero, namely the incident wave wavelength is exactly the same as the natural wavelength in the elastic tube. Then you see the first harmonic will grow steadily to a certain value. And the second harmonic is lower, third harmonic is lower. And now if the detuning becomes larger, then the amplitude becomes smaller. And not only that, there's this oscillatory phenomena. This simply means that depends very much on the length, where you cut off the length of the tube. If you cut it right here, then the amplitude gets very small, so not amount of energy can be generated. If you cut off here, the energy can be larger. So it's critical where you what the length of the tube that you want to choose. This is the effective detuning. Now, once the amplitude is found, harmonic amplitude is found, it's easy to figure out what the power flux in the tube, which is, of course, equal to the average pressure times the mean velocity. This turns out to be proportional to the sum of the amplitude squared. And the so-called capture width is this dimensionless ratio of capture width divided by the wavelength is equal to some sum of the harmonic amplitude. Now, with this, let me give you some numbers here. If, again, I want to see the effects of detuning and wall friction. See, when the wall friction is small, even with small detuning, this KW can be very large. 30, much bigger than 1, than that single, in comparison with the single buoy, okay? And however, if the detune is large, 0.5, then it drops. The detune is much larger, it drops further. Now this is the effective detuning. If affected the friction, it's also very, very obvious. Because with larger friction loss is large, then their efficiency to capture width is lower. This is a large friction, small friction. There are many other examples that we have, many other computations we have done, but we so far, I'm just presenting to you these two. Now this, I must say, this project is still going on at the University of Southampton. Whether or not it will be materialized in the future, this is not easy so far. But I consider this as sort of a neat problem that links, the idea was very interesting, and the fact that the mathematics is close to that, not only in optics, it makes it scientifically very interesting. Okay? Now, this is the first part of my talk. The second part is on blood hammer, which is probably, once I explain it, it's a very obvious, the relationship to engineering is very obvious. First of all, what's a blood hammer? Blood hammer is due to sudden blockage of blood vessel because of clot. Okay? Now, if you suddenly block a blood vessel, then acute pressure can rise, and which can cause intracerebral hemorrhage and rupture. And not only that, in addition to high blood pressure due to the waves involved, the high wall stress, shear stress will be created. Now, the effect of wall stress can cause arteriosclerosis lesion, rupture, and it can cause heart attack, stroke, peripheral arterial disease. This, the effect of shear stress has been highlighted by Dr. Xu Chen, the director of biological engineering at UCSD. He has done a lot of work on this type of thing. Okay? And, okay, now this problem was pointed out as very similar to a problem in hydraulic engineering. This is why this problem is hydraulic engineering inspired a study in biomechanics. In the former problem, it's the blood flow inspired engineering design. This is just the linkage is this way. Now, in a water pipe, suppose in the city water pipe, you have a valve somewhere. Originally, when the valve is totally open, there's uniform going through at a certain speed. But if you suddenly close it abruptly, then the acoustic wave will be generated. Acoustic waves is because the water is slightly compressible. Therefore, sound wave will be generated, which can cause rupture of the pipe, especially if the pipe is old. Okay? Now, there are theoretical studies on this in textbook. In the case, if you ignore friction, the wave is some sort of a shock wave of moving from the valve towards the reservoir. Okay? Now, the classical wave water hammer theory is the following. It's a wave, water pressure is governed by this wave equation, but it's resisted by a nonlinear friction law. Now, there's in usual water pipe, the friction law is, the friction is due to turbulence. Therefore, the friction law is modeled by some quadratic law with an empirical factor of F. But this empirical factor depends on the roughness of the pipe. And not only that, at the valve, the velocity is suddenly changed. Therefore, it causes a pressure gradient at the valve, which in the most ideal case, if the shut-in is very sudden, then the pressure gradient is a delta function of time. Okay? At the reservoir, which is completely open to the reservoir, the pressure is equal to 0. This is a crude assumption by neglecting the wave radiation due to sound. Okay? Now, because of this nonlinear friction factor, the usual method in standard textbooks on hydraulics is by a numerical method of characteristics. But in all these studies, it is usually seen that the damping is slow. In other words, damping time and oscillation time are vastly different. Therefore, this is a problem with multiple scales again. Okay, now, the problem I'm doing is the following. Now, suppose there's a large vessel with an artery like this, blood clot is someplace here. I want to assume this artery to be elastic, has an elastic wall. And also, I would consider the additional factor. Suppose there's a plaque due to some illness. There's a growth of someplace. Whether this plaque can have some additional effect. Okay. And this problem is very similar to that of a hydraulic problem. But the thing I want to make sure that there's some distinction. First of all, in usual blood vessels, because the blood vessel radius is very small, the flow is very often not turbulent, but laminar. And not only that, the frequency is depending on the length of the pipe. The frequency can be such that the viscous boundary layer is not large compared to the whole flow. Therefore, the Stokes boundary layer theory can be extended to this kind of problem. Okay, and now the equations of motion are this way. This is the conservation mass equation with instantaneous radius related to zero to the cross-sectional area like this, and the radius is the radius is r bar is the radius before dynamic, the static radius. And we assume the radius to be variable in space in order to account for plaque. Okay? And then in the biomechanics book is either to find the pressure, the relation between pressure and the distension of the radius. And with this kind of using this, it's possible to rewrite the conservation mass equation like this, and where C is called the Moen-Korfik wave speed in blood vessel, which is not a constant. Unlike that in water hammer, C is 1500 meters per second. Here, this velocity depends on the elasticity of the wall and on the thickness of the wall and on the radius of the wall. If the radius is varying from place to base, then C has to vary from place to base. Okay? And let me give you some numbers. Normal human artery, C is less than 10 meters per second. For dogs, 5 meters, 8 meters, and so forth. But according to Dasma, who's a physician, he stated that due to sclerosis of the arteries and so forth, and initial distension of vascular wall, and due to aging, the blood vessel wall can be stiffened. As a result, the wave velocity can be large. It can be as large, I must say, so far I found out this to be a very large number. It's 10 times to 30 times larger than the ordinary velocity in blood pipe. So we'll just consider the case, I want to consider the case of a very stiff artery and therefore high velocity. Now, high velocity, this is, as far as the flow is concerned, I have to work out the viscosity. Viscosity is figured out by looking at the local flow inside the pipe. Now, this local velocity, I assume linearity, it has a laminar viscous stress, and the average velocity is related to local velocity in this way. If you take the spatial average, the average velocity, the inertia and the pressure gradient and the viscous stress is related this way. And this can be found by local Stokes boundary layer analysis. And let me show you the ultimate dimensionless equation. This so far is a linear theory, is that the pressure is governed by this equation. Notice that the area, suppose the area is non-constant, it shows up in two different places. It shows up in the left-hand side, it shows up in the velocity c.
And there's a small, this last term represents a small viscous stress due to the wall. Okay, epsilon is a controlling parameter, which is essentially Stokes modular thickness divided by the mean radius, where the Stokes modular theory depends on the length of the artery and on the quotient speed when the velocity is uniform. Well, this equation can be, let me assume that the plaque is very thin. So far, we do not consider it, although in reality, the plaque can be very thick. It can be as thick as the radius of the blood vessel itself. So far, I'm considering a simpler case where the radius, the area is slightly different from the radius of the uniform cross-section. Therefore, the wave velocity becomes the linear equation, but with some small terms representing the effect of the plaque. Okay, now again, because we assume that even with a small wall friction, the damping rate is very low. So therefore, if the period due to the wave reflection in this finite length is a certain quantity, the damping time is much longer. As a result, again, this is a two-scale problem. With this two-scale problem, I introduce a slow time t, and then the first order, second order equations like this. Now, let me then just go to these. These are linear problems. Solution is in principle very simple. In particular, the leading order solution is that of a non-viscous blood vessel with initial condition, with the boundary condition that at the blood clot there's a time-varying acceleration. This, in principle, you can use a delta function, but we use a function which looks almost like a delta function, but with a small but finite duration of the blood clot. Okay? And at the end of the large artery or the heart, and the pressure is equal to 0. These linear equations at each order can be solved in principle. But let me simply point out that the leading order solution is very simple. It is primarily the part without this blue part. Okay? There's lots of sinusoidal components in time, and with this sinusoidal wave because of reflection. Now, nevertheless, in this, however, the leading order solution does not depend on the slow time. Let me introduce an artificial modulation amplitude, P of t, which is unknown. And I assume that initially this pt is equal to 1 when time is small. But as time goes on, this pt is going to be some function of time which is unknown. Now we want to find out what is the equation governing this solar modulation amplitude. Okay? And we can, from this solution, we can work out the velocity and so forth, so shear, and figure it out. And in particular, by Stokes modular equation theory, we can find out the coefficient in this expression that relates the wall shear stress and the mean velocity in the tube. Now, the interesting thing is the second order. First order can be solved by Laplace transform. Second order problem is interesting in that the Laplace transform, the inside the Laplace transform has a double pole. One is the first factor when s is equal to I km. One is when hyperbolic cosine s is equal to 0, which happens to be 0 at the same place. Therefore, this factor gives rise to a double pole. Because of the double pole, this Laplace inversion will be increasing linearly in time. Because we do not want the solution to be a double, therefore we insist on this time linear part be 0. As a result, we get a solvability condition which governs the modulation factor Pm, which is governed by this linear equation. This part, lambda, has to do with friction. This part has to do with the plaque, which is, because this part is complex, therefore the formation, the form of the plaque affects the phase of the wave, but the viscous friction affects the amplitude of the wave. And this equation can be easily solved. For any given platform, I can easily evaluate this alpha m analytically. As a result, the solution from here on is analytic, and so first order, second order are all found. Let me just give you some results. Now, first of all, we don't have experiments for this kind of experiments. First of all, with plaque, there's no laboratory experiments of measuring the rheological property of the plaque. The plaque is formed, but its material may be very different from that of the vascular wall. While the vascular wall can be very stiff, the plaque is some sort of particle stuck together, which may be very soft, much softer than the wall itself. So in this theory, we ignore the rigidity of the plaque, but we account for the thickness of the plaque that blocks the limits of the area. Okay? Now, we first use this theory to compare with the existing experiments in the water pipe done in 1960 by two mechanical engineers. These people use a steel pipe with water. They create a water hammer problem, and the steel pipe is 120 feet long, the radius of 1.5 inches. They use a viscous fluid which is 50 times as viscous as water. As a result, they made sure that the flow is laminar in the pipe. And the only thing they did not make clear initially is the duration of the impulse. Okay? We made some trial and error in order to find a proper duration of the shut-off in order to match with the experiment. You see that this is the time series of the pressure measured at the midpoint of the pipe, x equals 0.5. The agreement between theory and experiments is pretty good. And then this is at the end of the pipe, at the valve. At the valve, you see that at the valve, the pressure initially is very low. Initially, because it's very far from the valve, initially the pressure is equal to 0. The match is pretty good so far. So we consider this to be a validation of the analytical theory, at least for the simple case. Okay, now we have computed time series of blood pressure. These are the examples where the plaque occupies 1/2 of the blood vessel, close to the blood clot. The 1/2 section close to the heart is smooth. And we find that the blood pressure is high, very high, near the clot, which is natural, because when you suddenly shut up the close the blood flow, the blood flow has to be stopped instantaneously at the point of the clot. Therefore, the pressure is high. The pressure is very high there. But very close to the end, close to the heart, the pressure is very low. You see, there's a decay in time. First of all, there's a decay in time. Secondly, depending on where you are, this is very close to, very far from the blood clot, right next to the blood clot. The variation is like this. We also have computed, this is a snapshot of blood pressure. Because this is a finite length, the waves moves like a step function. First of all, it moves from the blood clot towards the heart, and then at the next half, this is the second half of the period, and goes back, it goes back and forth, back and forth. We have just plotted 4 quarters within one period. There are many periods where the amplitude will decay. Okay? Now, we have also computed this series of the shear stresses. The shear stresses is up because the shear stress at the clot, because the flow is stopped, the shear stress is small, 0. Whereas the shear stress at the other open end, because the fluid motion can be very free, therefore the shear stress is large. So this is the difference between the open end of the blood vessel and the closed side of the blood vessel. And this is the time series of the shear stress. And finally, this is a snapshot of the wall shear stress. These things are so far theoretical, as I said, so far we have found no experimental verification for this kind of thing. I'm not too sure this is easily done in the real situation, not easy. Probably experiments must be done in rubber tube, in artificial surroundings again. Now, this is, even though we have done many other numerical computations, but let me say that the problem for this has lots of future work to be done. First of all, the blood clot can be very thick, okay? Therefore, the area reduction can be very large. Not only that, so far I know of nobody who has measured the rheological property of the plaque itself. Is it the same as the blood vessel wall, or is it different? These are important before further advances theoretical modeling can be made. The theoretical work that involves at least new equations for thick plaque, and the equation will be changed because the radius is not the radius is comparable to the thickness. It involves wave scattering and so forth. Linear and nonlinear effect can be there can be a lot of things that can be resolved can be pursued in the future. Okay, so this is all I have. As I said before, especially this problem, biomechanics problem, to me is new. So this is if I say something wrong in biomechanics, please forgive me. And well, I thought these problems are interesting. They're related way, and I want to take this opportunity to welcome Ken. And not only that, because of his relative youth, I welcome him as a freshman of the member of the Golden Age. Thank you very much.
I think Chang has just demonstrated the advantages of being an applied mathematician, that you can move from ocean engineering to biofluid mechanics almost in the wink of an eye, or an epsilon. Questions? I think we're a little bit behind, but I think we have time for one question.
John Patterson did a PhD thesis on the blood flow.
Sorry?
John Patterson.
John Patterson?
Would you know him?
No, I don't know.
I'll put it in contact with you.
Okay, good, thank you.
Any other comments, questions? Thanks, Chang.
Thank you.